Hi, thanks Rebecca. It's a pleasure to be here today in a room with so many smart, creative people. Thanks for letting us come here today and talk to you. We're really excited about it, and we're really excited about the contest that Rebecca referred to. So I am a scientist, I'm not an artist, but nevertheless I want to start by showing you some of my favorite art and some of my favorite artists. This is one of my favorite sculptures. It's called Winged Victory. It's in the Louvre in Paris. I really love this piece because of powerful form and graceful contours, and the way the artist was able to take the stone and carve it in a way that suggested power and movement of this figure. I'm a big fan of Impressionism, and this is one of my favorite pieces by Auguste Renoir. This piece I love because of the color and the light and the way that the artist was able to capture so much about this moment in time using so using so few elements in the art. Changing gears a little bit. So this is one of my favorite artists of all time in any category, and obviously one of the best guitarists of all time, Jimi Hendrix. All right, I didn't know that was going to work with you guys. I am happy to hear that. So, when I listen to Jimi Hendrix, it's not just that you hear it, you feel the music, and for me, I can almost see it. Finally, this is a powerful lead from my favorite ballet, Swan Lake, and I really like the power and grace here, the integration of the dance and the music. It looks like it's so difficult to accomplish, but when it's done, it's one of the most compelling art forms, I think. So, what happens when we watch these things? How do we actually perceive these works of art? When you're watching these things, or your favorite things, it feels like it's immediate. It feels almost like it's magic, like there's nothing in between the performer and you. But it's not magic, and it doesn't happen immediately, although it does happen pretty fast. It happens in a complex set of interactions in one of the most beautiful and complex devices that we know of in the universe, the iPhone. Okay, no, it's not the iPhone. And just to be politically correct here and not offend anybody, it's not this either, it's not a galaxy. And no, we're not all actually living in the Matrix serving the machines. Actually, it's inside of this. This is where all of that happens. Inside of this 3 pounds of biological stuff, this is the thing that's responsible for your perception of that artwork and for your perception of everything else. This is the real matrix, the biological matrix, your brain. So I'd like to talk to you today about how you get information into the brain and a little bit about how information is processed in the brain, how it works when it's going right, a little bit of what can happen to make it go wrong, and then about the relationship between neuroscience and art, and a little inspiration by showing some artwork at the end that maybe will give you some ideas of things you could try. So neuroscientists don't use the kind of artworks that I showed you at the beginning when we're trying to understand the brain. We usually use very simple things, a simple bar on a piece of paper on a computer screen, or a very simple moving stimulus. And we see what pattern of activity is induced in the brain by those stimuli and how it's related to our perception. Every 4 years or so, we do use some more complicated stimuli and see how those affect the brain as well. So, what you may not realize is that there's a lot of similarity between what you do, between what artists do, and and what we do, what scientists do. And what I mean by that is artists, no matter what your original media is, whether it's sculpture or dance or film or painting, ultimately what you do is change activity in the brain of your observer. And that's what we try to do. We try to use simple stimuli and change activity in the brain and figure out how it's related to perception. Really, both of us are trying to understand how the brain works and how we perceive the world. We want to know more about our perception and more about what it is that makes us us. So before I dive into the organization of the brain, I need to introduce you to the basic elements that construct the brain, and those are neurons. Neurons are cells which have a cell body that contains the nucleus, and then, I guess I should use the pointer, and then dendrites, which are arborizations or tree-like structures where all the input comes into the cell, and the cell integrates that input and then sends outputs on an axon to other cells downstream in the brain. And when we study the brain, we try to record from these cells and figure out what they like. We say, what does this cell prefer? And what that means is we try and show a stimulus, say a bar on a computer screen, and record from a cell using an electrode or using some sort of imaging device. And we figure out, does that cell give a lot of action potentials, a lot of impulses of activity when we show this stimulus versus show this stimulus. And we would call that then the preferred stimulus. This cell likes vertical. So cells like this pyramidal cell from the cerebral cortex interact in complex networks. They talk to all the neighbors around them and to cells that are far away. And the way this works is that a cell fires an action potential, an impulse of electricity, and it sends that out its axon to all the cells that it's connected to. And there's a synapse, or connection, which is a chemical transaction that causes excitation in the next cell. And if only one of these cells is talking to this cell, then probably this cell won't do anything. But if more cells are talking to it at one of the thousands of synapses that each cell could receive, then this cell might also fire an action potential and continue a cascade of activity in the brain. So that's a very brief introduction to the neurons that make up the brain. And now I want to take you on kind of a quick whirlwind tour of what happens when you see something. What actually happens when we see something in the world. What I want you to do is watch the screen for a second and tell me what you see. Okay, it's easy, and it's easy even if I show it for only a fraction of a second. It's very easy for you to identify that you saw a blue butterfly on the screen. But what really happened to get that information into your brain and for you to be able to see it? So when the stimulus was put on the screen, energy on the screen ultimately came to your eye and was converted into electrical energy and then communicated through the visual system to the cortex, where specific patterns of activity allowed you to see the butterfly, and you say, I see a butterfly. Simple, right? So far. So if you instead, the butterfly was displayed on the screen, but something went wrong, something prevented transmission of that electrical activity to the cortex, and that pattern of activity was not found in the cortex, then you will not see anything. You'll say, Bill, what are you doing? There's nothing up there. So it's this pattern of activity in the brain that is correlated with what you see. It is what you see. What happened there in the brain is your real world, not what happened out here on the screen. So I want to briefly now tell you a little bit more about how that signal actually gets into the brain and gets processed. So light is electromagnetic radiation. The part of the light we can see, about 400 nanometers to 800 nanometers, or visible light, comes from the sun, and it comes as white light, meaning it contains all the wavelengths that you can see. When it hits the butterfly, some parts of the light are absorbed, and other wavelengths are reflected and continue onto your eye. The part that continues is the part you see. In this case, the blue light is what's reflected off the butterfly. It's focused by your cornea and your lens onto the back of the eye, the retina. And it actually travels through all the tissue in the retina to the light-sensitive cells at the back of the retina that are the rods and cones. And within those photoreceptors, yeah, you can't point at it, Bill, you have to use the... So within those photoreceptors, there are discs that contain special molecular assemblies that capture photons of light and initiate a cascade of molecular events that close ion channels on the cell membrane, create a voltage which is transmitted down the cell, which causes the synapse to be active, a chemical event. And that activates these later cells in the pathway, and finally a spike, a neural impulse, leads on the retinal ganglion cell headed out towards the brain. That's a very brief introduction to phototransduction. The rest of the visual pathway is shown here, two different views. This is the base of the brain, the bottom or ventral surface of the brain, and that's where the visual pathways are. The retinal ganglion cells continue towards the middle of the brain. They contact a structure known as the thalamus, and then there are axons that leave there and form a big sweeping arch of a mass of cells that go to the visual cortex. This is called the optic radiation. So from the eye, eventually the information comes back here to the primary visual cortex. You can see that on this brain, if I don't destroy it. The visual cortex is mostly on the interior, on the back of the brain, here in the occipital cortex. And I always carry a spare. Yeah, here's mine. This is about how big your primary visual cortex is. It's about the size of a credit card, 4 by 8 centimeters, or about 3 millimeters in width. It's a sheet-like structure with many layers. It contains millions of neurons, and but it's not just a mass of jumbled up wires. It's actually a very organized circuit. So here's the back of the occipital cortex, and we can pull out and flatten the primary visual cortex. And as I said, it's like 4 by 8 centimeters, 3 millimeters in width. It has layers. This is what one of those cells would look like actually in its home here in the cortex, with dendrites that reach across this width and we receive input from thousands of other cells. So there's a lot of order and structure in the brain and in the visual system at lots of different levels of organization. One of those is that the visual world in front of you is represented in a very orderly fashion in the back of the brain. So if you were staring straight ahead at this spot, this blue area would be represented in this portion of the brain, and it would take up actually this much of your primary visual cortex, even though it's a very small area. It's because you overrepresent the central part of vision. This is where you have the most acuity, it's where you have the most photoreceptors, and it's the part of your eye that you use the most when you look around a room and you look at people's faces or other things in the room and try to identify things. So a huge amount of the cortex is devoted to representing that. So there's this type of order, but then there's several other types of organization that are interesting and I think also beautiful. I should say, obviously I don't expect you to get all these details. What I'm hoping is that you get a feel for the way that there's organization at all these different levels of scale, and the way that there's beauty at all these different levels within the visual system and the brain. So this next type of organization is called ocular dominance or ocular preference. The inputs from your two eyes are initially kept separate in the brain until they reach later stages in the cortex. And when they come into the primary visual cortex, there are cells that respond primarily to the left eye or to the right eye, And they're found in groups, like say this whole row of you responded only to left, and this whole group responded only to right, and that group again to left. Then we'd have knock-over dominance map here in the audience, like you have in the brain. So there's these stripe-like structures for which eye the cells respond to. And then there's also another interesting feature called orientation selectivity, which is shown here. So your brain is not just passively viewing the scene in front of you, it's taking out specific elements of information and trying to construct something. One of the things you try to find in the visual scene are contours. And there are cells in your brain that respond to contours of a particular orientation, say horizontal, like this. And you could find columns of cells indicated here by the dark bands that all responded to this orientation. And if we change the orientation slightly, then you see there's a slightly different pattern. And we change it slightly again, there's a slightly different pattern, and still for this orientation. So in this way, orientation is mapped across the cortex. Again, if you guys preferred horizontal and you preferred 22 degrees and you preferred 45, we'd have an orientation preference map in the audience. And you can indicate those with color. Here, color shows which cells prefer what orientation. And they make these beautiful quasi-regular structures. So that's some of the organization there, and one thing I've tried to show you is that cells in a given area, they have the same preference, like they all prefer horizontal and they all prefer one eye. But they also communicate with cells that are far away from them by horizontal connections that extend for millimeters across the surface. All of that was about one visual area in your brain. You actually have somewhere between 10 and 30 visual areas that process information. Here they're indicated in blue on the lateral or outside part of the brain, or the medial or inside part. And this is a flattened human cortex, the whole cortex. And you can see that vision takes up about a third of your cerebral cortex. So it's very important to us and to all primates. And within this, there are lots of different types of areas. And they all have the same kinds of principles. The world is mapped, and lots of different features about the world are mapped, say color or faces or motion, are all mapped in the same kind of way that I showed you those other maps. So this is some of the specific areas for vision, and I just want to take you on a kind of a quick tour of what some of those different areas do. There's two basic processing streams in the rest of the visual cortex. One deals with where you are in the world, where things, objects around you are, about spatial location and about where you're going in your environment. And then the other path deals with what you're seeing, what type of objects they are, what color they are, if it's a face, if it's a house or a bike or something like that. And they're called the what and the where pathways. So MRI, functional MRI, which you guys may have known about, you've probably all seen images in the paper or on the news about, here's an MRI experiment where they saw if people who preferred Coke were different than people who preferred Pepsi, or people who liked Obama were different than people who liked Romney, by looking at their patterns of activity in the brain. But this is an example of one of the really basic experiments that can be done to find motion responsive areas in the brain. And if you could click that, please. Thanks. So people are put inside this magnet, lying horizontally, and their head is held stable. And they view a moving stimulus, say a stimulus that's moving like this, or one that's moving left-right, or the checkerboard pattern that you saw there that was flickering. And then specific areas of the brain are active while the person is viewing that. And I'm not used to this, sorry. And we can identify those areas that are responsive to motion. And in the case of motion, it's an area on the lateral surface of the brain here that responds to this type of motion. There are many other kinds of motion, such as optic flow. This is the kind of motion you get when you're moving through the environment, like on a bike or on an airplane, as they're showing here. And there's another area of the brain that responds to that. And even for biological motion, i.e. for motion like a human walking in a certain direction, if you take lights and put it on a person and capture their movement, say while they're dancing or kickboxing or walking, you can find areas of the brain that respond very strongly to this stimulus, even though there's very little information in the stimulus. So clearly, this area of the brain is involved in trying to capture elements of what's in front of you and put it together to a symbol that there's a moving person there, or a person running at me or running away, or some sort of important biological motion. The last type of selectivity or special area of processing that I want to show you is that there are areas of the brain here on the ventral or bottom surface of the brain. Basically, I have to take this one apart. Down about here on the brain. There are areas that respond selectively to faces and not to other objects. And people who have damage to this area can have a very selective inability to name faces, even though they can see other objects and they can say that's a banana, or they can drive, or they can walk around. But nevertheless, when they look at a person like Rebecca, they say, hey, I don't know, there's something there, but I don't know what it is. They can't name what it is. And damage to some of the other areas I showed you there, like for motion, the same sort of thing can happen. People have damage to areas that respond to motion, and they report that when you're pouring coffee or water, they see it frozen, like a frozen waterfall. And they see cars moving or people moving. They don't see them moving, they just see them like jump to different positions. And you can imagine how horrendous it would be to try and live your life that way. So there's real selectivity in the brain in these different areas. Multiple areas are involved in everything you do, but there is real selectivity. How are we doing on time? Okay, thank you. So I want to briefly just show you that the kind of organization that I showed for the visual system is also found in other senses that you have, for example, touch. When something hits your finger, say a sharp probe or a pencil, you get a deformation or changes in the membrane of the cells there in the skin. And the cytoskeleton in those cells pulls on channels, which opens them and causes voltage changes in the cells. And they fire action potentials, and as with the retinal ganglion cells, those action potentials eventually make their way through the spinal cord and up to the brain. And in the cortex, the organization that we saw in the visual system is very much the same here. Now, instead of the world in front of you, it's the surface of your body that's represented in an orderly fashion across the cortex. So right here on the middle of the lateral surface, if you took a slice through that section of the brain, you'd see this orderly map of face, hands, arms, and torso. You'll notice that much more space is devoted to the face and hands than to your torso, and as with the eyes, that's because you have more receptors in your fingertips, and because you use them to explore the environment. You move them around to touch things if you're trying to identify something. The same way you move your eyes around when you're trying to identify something with vision. So there's much more representation for fingertips. So, I'll tell you, just a second. Sure, wait, great. So, before I show that, so far I've tried to show you a little bit about how you get information into the brain and some of how it's organized in very specific ways in different areas of the brain to process different kinds of information. And that's what happens when it goes right. There are lots of things that can go wrong, and they're kind of revealing and showing what it is that you really do with the information that you're receiving from your senses. One demonstration of this is this experiment. This is an experiment that deals with attention. In this experiment, the observers were instructed to watch this white team and tell how many times they passed the basketball. So the people are moving all around and they're passing the basketball back and forth. The people in the other outfits are moving around also, and it's very hard to track, and you're following the basketball around. While that happens, this person in a gorilla suit walks through the scene. And you think, right now for you, easy. Easy because you weren't doing the task. Because you weren't trying to follow the basketball around and count how many times it was passed. If you were doing that and you'd never been told about this experiment, 50% of you would not have seen the gorilla walk through, even though it walked right through the middle of the scene. I can tell you that I felt for it the first time when I saw it in a talk. So it's very powerful. What you see is not everything that's in front of you, it's what you're attending to. And that's a very important thing to know. So another demonstration of this is shown here. This is an ambiguous figure called the Necker cube. It's really two-dimensional, right? It's only lines that are drawn on a piece of paper or on a screen. There's nothing inherently three-dimensional about it, but all of you see something three-dimensional when you look at it, I assume. Anybody not seeing three-dimensional? And it should flip back and forth between two alternative possible visions of it. Why do you see a three-dimensional object here instead of something flat? You see it because when this happens in the real world, usually 99-point-something% of the time, it really would be a cube. This configuration doesn't happen naturally on flat things, and your brain knows the statistics of the world and uses that information to make guesses about the objects that are really out there. The goal of your visual system is not to have an accurate pixel by pixel, high definition view of the world. The goal is to find objects that are out there and try and be able to use them. This is another example where, what do you see here? I hope you see Pac-Man and a square. but there is no square, right? The lines of that square are not defined in the middle, but it looks like there's something on top of a set of four circles. And that's the configuration that would normally happen in the world. So you complete those contours to form a square in your visual cortex. One other powerful example here that what you see is not really what's right in front of you at one specific point on your eye. What color are these two spots? They're the same, and they're this color. I'm sorry, this one. They are both this color, and for me it's still hard to believe that unless you actually do the experiment, which is take a cutout of a piece of paper or something else and block the rest of it around it, and then you'll see that they actually are the same. What's happening is that your visual system is interpreting the illumination of the scene and where the light and the shadows are and the other three-dimensional information and projecting what the illumination of that spot should be based on the total information that's being given, based on the surround and what hit the retina at that spot. So this example is an example of an unfortunate condition that happens to people who have amputations or who lose limbs in accidents. There's a condition known as phantom limb. What this means is that although the person's limb is gone, say their arm is missing after an operation, they still have the experience that it's there. They still feel that it's there. They feel usually pain coming from their arm, the arm that is no longer there. And it can be a very devastating condition, and it can be very hard to treat with any form of regular pain treatment. And what this tells you is your perception of where your body is, like your perception of vision, it's not just dependent on the receptors from that part of the body, it's dependent on what's happening in your cortex. And probably those areas of cortex that used to respond to the arm are now getting information from other areas. And in fact, people have shown that if you stimulate the face in these patients or the shoulder of the remaining part of the arm, that people report when they're stimulated there that they feel it in the missing arm. And one reason that may be happening is that those areas are next to each other in the cortex, and they may be receiving connections from those parts of the cortex. Last example, this one not as morbid, but just as crazy. This is a condition called as synesthesia. In synesthesia, two different senses interact. There are people who, when you touch them, they see blue. When you show them a cube, they think happy, or they think that shape is sad. They hear a sound and they think it's brown. And one of the common forms of this is that people see letters intrinsically in one color. So you show them a letter that's not colored, and they automatically see it as colored. Say every time this woman, this is a drawing from a synesthete, a woman who had synesthesia. And she made this drawing to show how the letters look to her. C's are always blue, Z's are always orange or red. And the areas of the brain that are involved in processing letters, and processing color, are probably close together in this region, and it seems like that this area of the brain, B4, which is responsible for a lot of color processing, is abnormal in these patients or receives an abnormal number of connections from other parts of their brain. So all of us are trying to see patterns in the world and form connections between the senses. They just do it in a more extreme, slightly aberrant way. Sometimes it actually turns out to be useful for them in some ways. And many of them are artists, actually. So I started out trying to have us look at what is the basis of our perception. And I hope I've convinced you or intrigued you a little bit that the basis of our perception is brain activity. That specific patterns of brain activity are involved when you see contours, or when you see faces in color. When you hear music, I didn't talk about the auditory cortex, but probably Hendrix playing a song here activates your auditory cortex and probably some language areas. And viewing this ballet probably activates motion and biological processing motion areas in your brain. This is way oversimplified. Probably in each of these cases, in fact, even in the simplest cases, multiple brain areas are involved, and the exact interaction between them changes very rapidly over time. All the visual processing I showed you, like for the butterfly or for faces or motion, takes like 200 milliseconds, a fifth of a second. That's how fast you can identify something. So although it's a complicated cascade of information, it happens very quickly. But at least this is a framework to think about it. In the remaining time, I just want to show you some of the many ways that the brain has been used as inspiration for art or has been used as art itself. And the first set of images I'll show have to do with the fact that you should really consider the brain part of nature, that part of what we do as scientists is describe it like we would describe trees or birds or anything else. Here, this is a drawing of a pyramidal cell made by a neuroscientist 100 years ago. I thought it looked strikingly like this tree from the savannah. And if I color it, I can make it look even a little more that way. Here, this is a stand of aspen trees on the right. This is a stand of pyramidal cells stained in the brain. I think the dendrites of these and the branches look very similar. The spacing of these apical dendrites in these tree trunks are very similar. Here's a tiger with stripes, and I showed you the brain has stripes and spots as well. If I color it, I think it looks a lot like the tiger. Now, this is my favorite section. It's not only natural objects that are similar to brain organization. A lot of man-made things are similar and interesting to compare as well. I like to think of the visual cortex as a cathedral. And this is a cathedral in Paris, and it has these flying buttresses or supports on the side of the building. I think of the optic radiations as being those side supports. And in the visual cortex, the maps that I showed you, I think of as being like the stained glass window in these cathedrals. The light comes through these and eliminates patterns in the brain. Finally, for this section, these are 3 maps that we made in our lab of brain organization. And these are 3 periodic tilings of the plane done by N.C. Escher, another one of my favorite artists. And I think they're very interesting to compare. Note that these are not really crystalline or regular division of the plane like these, but I think these patterns are very similar. And finally, just want to show a gallery of real images and brain-inspired images. So the first image I showed you was a neuron actually growing on a silicon chip. This is an image of a retina where retinal ganglion cells are stained in red and blood vessels are stained in blue. It doesn't even look real to me. It's amazing how these 4 stains on this retina make the retina into a work of art. This is another scientific work of art. This is called a brain bow. It's a mouse that's been engineered to have randomly different colors and cells in a particular area. This is in the hippocampus, an area that has to do with learning and memory. And we can use that to study the connections of particular cells, but it's also just beautiful. These are 2 drawings of pyramidal cells by a neuroscientist who's also an artist. I love that he's drawn these in black on paper that has some texture and kind of an Asian theme. This is a drawing of his of the hippocampus. This is a more abstract piece that has to do with pyramidal neurons and this kind of connectivity in the brain. And then some larger scale abstract images of the brain. People also take their data and make images that try to capture something about the data in their experiments. Finally, this is a set of artwork done by people with synesthesia. The drawing on the left is a woman who's trying to indicate the experience, the visual experience she had while she was receiving acupuncture. So she saw red light with green highlights while she was doing that. This photograph on the right, the woman in this case who also has synesthesia, her mechanism is to walk around the world, wait till she has a synesthetic experience, and then take a picture and try and capture what it is that triggered her event. Lunchtime. So, I've tried to tell you a little bit about the brain and about its relationship to art. Now it's your turn. Make something that produces activity in my brain that makes me go, wow. And at least, thank you for your attention.